Hello, we are in section 3.3 and we're going to tackle our second objective, which is curvature. But before that, we're going to take a look at some theoretical aspects of arc length that will help us define curvature. And once we define curvature, we'll look at some shortcuts or easier ways to try to express curvature, because it's not really that easy of a formula to kind of get at through the definition. So let's get started. All right, we talked about the arc length and what that means, but we're going to take a look at this idea of parameterizing by arc length. Now, before we get through all this rhetoric and all these statements that are listed here, let's talk about the circle, because that's usually one of the easiest things to talk about. And we've seen that that circle can be parameterized with r of t, going cosine t, sine t, and then this is going to go from 0 to 2 pi. And ideally that's the best parameterization for the circle, because 2 pi would be the length of that circle, and when you parameterize it, you essentially get that exact value. However, we can also reparameterize this a different way. R of t is equal to, let's call this R1 of t, and this is equal to let's say cosine 2t sine 2t. What this gets us is the circle, and if we go from 0 to 2 pi, we would draw the circle twice. So if we want to just capture the circle one time, we just go from 0 to pi. And the thing is that we can change this constant 2 to any number, and we can even put different functions in there, strangely enough. We can put like r2 of t is equal to cosine t squared sine t squared. And so if we want to draw the circle just one time, well, we can go from 0 to whatever makes this t squared equal to 2 pi. So I think that's going to be the square root of 2t, or square root of 2 pi. In any case, there are an infinite number of ways to parameterize any curve that we're talking about. Okay, it's just a matter of controlling the limits and things like that. So the idea of this arc length parameterization is to parameterize a curve in a certain way that has a very special property. So let's read through this rhetoric here, the paragraphs. So we have formula for arc length defined by vector valued function, and take this a step further, and let's call this formula an actual function. So I think we've done this in calculus 1, where we took the integral and make a function out of it. So a vector valued function represents a position of the particle in space, and a function of time. Then the arc length function measures how far the particle travels as a function of time. So the formula for arc length follows directly from the formula from the formula for the arc length function is taken directly from the formula of the arc length. So now we're making this as a function of t. So your arc length formula, to make that a function of t, we're going to make one of the limits, the top limit, to be a t value, the parameter. And that means we need to just change the dummy variable inside. Oops, I don't know what happened here. We're going to change the dummy variable inside here and call it a u. And so the actual parameter that we're looking at is t for this particular function. So again, I think we've seen that before by making this top limit to be a variable of a new function, a new integral function. Then we have that. So if you have a curve, if the curve is in 2 dimensions, then there's only 2 terms up here under square root. And the reason for using this independent variable u is to distinguish between the time variable, the t variable, and the variable inside of the integral. So since s of t measures the distance of the function of time t, and then s prime of t measures the speed of the particle at any time t. And then we have this formula. So let's take a look at this formula. The derivative of s is going to be d dt of this integral, and we know from the fundamental theorem of calculus that the derivative of an integral function, where the t variable is a top limit and then the a is just whatever constant that is going to be whatever is inside that function. So remember, we found a way to write the integrand in a lot more compact way, and that's the magnitude of r prime. And so here the derivative of an integral is going to be the original function, which is just the magnitude of r prime. Okay, so that's really interesting. If we assume that r prime defines a smooth curve, then the arc length is always going to be increasing. So there's no funny things happening there. Our arc length is increasing because this is always positive, and we're going to go from A to B integrating this, and then we're going to get that. So s of t is always bigger than 0. S prime of t is always bigger than 0 for t bigger than a. And then if r of t is a curve where this is equal to 1, the magnitude of the derivative is equal to 1, then s of t is just going to be equal to this. So, which means that t represents the arc length itself. So what we're saying here is that we want this t value we want this way of parameterizing this particular curve to be the actual arc length. Okay, and again, our first example over here is the arc length formula already given to us. So when we integrate this, it's going to give us whatever the top limit is. It's going to give us the actual length. So this is our theorem. Let RT describe a smooth curve for t bigger than some value a, whatever the lower limit is. Then the arc length function is going to be given by this formula. S of t is equal to the integral from a to t of the magnitude of r prime of u du. And then further, the derivative of s is going to be just the magnitude of the derivative without the integral, and that's always going to be bigger than 0. And if r was actually equal to 1, then the parameter t itself represents the length that you're looking for. Okay, so let's show that this actually works for for this parameterization. R of t is equal to cosine t sine t. And so we do the derivative of that, we get the magnitude of the derivative. So let's first find the derivative. R prime of t is equal to just the derivative of cosine, negative sine t, derivative of sine, cosine t, and then the magnitude of that is going to be the square root of sine squared t plus cosine squared t, which is equal to 1. So that's perfect. And then we note that s of t will be equal to the integral from 0 to t of 1 du. And whatever we put in for t here will give us the exact arc length. So let's say t is equal to pi. Then we look at the length of the circle that ends at pi, and that is the arc length is going to be pi. So that's half of the circumference. Okay. So that's we've been kind of taking that for granted, but there's something special about that parameterization because it's already parameterized by arc length. So if somebody else gives you a different parameterization for the circle where your limits don't go all the way up to 2 pi, then you're not parameterizing by arc length. Okay. So let's take a look at this example. Find the arc length function for this helix. So and then let's go ahead and add something to this. Let's reparameterize that. So then reparameterize the helix. Okay, so let's find the arc length formula first, and we'll begin by just finding the derivative of r. So this is going to be -4 sine t, 4 cosine t, and 1. And when we take the magnitude of that, and we will get -4 sine t squared plus 4 cosine t squared plus 1 squared. This is going to be a sine and cosine with a 4 factored out. 4 plus 1 is 5, so this is going to be this is 4 squared factored out because the t squared should be inside. So that would be 4 squared, that's 16, plus 1, 17, and you can't take the square root of that. So it's just going to be the square root of 17, which is great. So now that we have that, that is your r prime t parameterization. So the arc length function is going to be s of t will equal to the integral from t is equal to 0 is a starting point, and then this could be any t value that we want to end, and then our r prime of t, which is square root of 17 du. Okay, and then you just integrate. So this is going to be square root of 17t of 17u, so square root of 17 times u, going from 0 to t. When you put 0 in, that's gone, so this is just square root of 17t. And then that is your arc length parameter, or that's your arc length function. And that's to say that to find the arc length from 0 to 2 pi here, you would just put t is equal to 2 pi in here instead of reintegrating it. And then if I want a different problem going from 0 to t is equal to 7, then I would just put 7 here, and then that would be it. So that's what makes this arc length function kind of handy. So now if we want to reparameterize this so that it's parameterized by arc length, let's answer the second question over here. To reparameterize by arc length, we're going to note that your s function and your t function is related this way. And then currently your parameterization is with t. And so if your parameterization is with t, we can change this so that we change the parameter into an s. So then this will lead us to a t is equal to s over 17. And so to change this and reparameterize this so that we have our parameterization with an s in it, we can simply put this in, replace this for the variable t. So now your reparameterization, and usually when you reparameterize, so you're parameterized by arc length, you're actually changing the parameter as well instead of a t to an s. So our function will be 4 cosine. Now instead of a t, we're going to replace that with an s over root 17. And then we have a 4 sine s over root 17. And then we have just the root s over root 17. So now that's reparameterized by arc length. Which means if we put this into the arc length function, we should get, instead of square root of 17, we're going to get 1. And then whatever we put in here for the derivative and then the magnitude of the derivative, that'll give us the actual arc length. Alright, so all this stuff is all theoretical, and it's not this finding this reparameterization is not the easiest thing in the world. This is easy because we're dealing with a helix, and in general circles and helices give us nice derivatives and magnitudes of the derivatives. So we just use these to illustrate what is theoretically possible, but practically looking for a random curves reparameterization, it could be quite difficult. Alright, so now getting to our main objective, which is looking at the curvature. The idea of a curvature is trying to figure out how something curves. So let's just draw a random curve. This could be in space or not in space. So if we draw some random curve that maybe looks like that, we can see that in certain places, like in this place, it's fairly flat, and then over here it gets a little bit curvier, and then it flattens out again, and over here it gets super curvy, and then over here there's another curve over here, and then this one flattens out. So just think about driving a car and how much you have to turn in your drive is kind of like how curved something is. Well, how are we going to measure how curved something is? The idea is that we want to reparameterize the curve so that it's parameterized by arc length. That kind of gives us a stable like a stable way, or a uniform way, a standard way of measuring how things happen in the curve. And then what we're going to look at is the unit tangent vector. So we're going to take a look at the unit tangent vector, and we're going to ask ourselves, how much is a unit tangent vector changing? So it's the rate of change of the unit tangent vector. And by normalizing it, and I'm just kind of using normalizing to say that we want this to be kind of standard normalized, so that it's the same measurement for whatever curve you're looking at, we're going to use the parameterization by arc length. So looking at how things curve, if we take a look at somewhere over here, maybe this point over here, a little bit before it, a little bit after it, we see that the tangent vector doesn't really change much. So this is going to have a low curvature. Now over here, if we're looking at a particular point a little bit before that, a little bit after that, we see that the tangent changes a little bit more drastically than the first point that we looked at. And so we should have a higher curvature. And then just to kind of make the difference here really very clear, you got tangent vectors that are going in one direction, and it makes abrupt changes to go in another direction. And so that's going to show you a higher curvature because the rate of change of your unit tangent vector is a lot more where it's curving more. So the definition for the curvature is going to be the rate of change of the unit tangent vector when it's parameterized by arc length. Okay, now unfortunately this idea of parameterizing by arc length is extremely difficult, and now we need to find the unit tangent vector, and that gets even more difficult. So the whole idea of computing this based on the definition is not going to be very easy. So what we're going to do in this next theorem is to look at alternative formulas for curvature. So there are several formulas, alternative formulas for curvature, and let's take a look at all of them. So if you have a smooth curve given by a parameterization r of t, then your curvature, by the way, the curvature that they use here is a Greek letter kappa. So it looks like a K, of course, but it's not. It's kappa. And it's like the rho that we may have seen before. Rho is like the Greek letter for R. It looks like a P, but it's really rho. So this is looks like a K, but it's really kappa. So one way to express this derivative is it's the derivative of the unit tangent vector with respect to any parameterization t, but instead of the ds in the bottom, we have to compensate for the change in parameterization. So the ds in the bottom would be the magnitude of r prime of t. So that is a slightly easier way of figuring that out. But sometimes finding the derivative of t is not very easy, as you may see later on in some of your computations. And so here is another formula that we can use. So it turns out that this formula is equivalent to the magnitude of the cross product of r prime and r double prime, and then we're dividing it by the magnitude of r prime of t. So how they got from this formula to the next formula we won't really go over because it's a little complicated, but let's not worry too much about that. And I usually try to tell people that cross product, use it if you have to, but it's usually the more difficult formula to use. But in this particular scenario, finding this cross product is actually easier than finding the derivative of a unit tangent vector in some cases. So sometimes those unit tangent vectors can get a little tricky, and then you take the derivative of that, and you got a big mess in your hands. So it turns out that this is, for most problems that you'll run into, using this curvature formula is the easier option. Now this is a more of a special case instead of an alternative. If you have a function y is equal to f of x, so this is not in parametric form anymore, or not in vector valued form anymore, but this is our old friend from pre-calculus, y is equal to f of x, and then you have the first and second derivative that exists, then the is going to be given by this formula. Now to go from this previous formula with a cross product to this new formula over here, there's actually a bridge that we can take. We can parameterize this We can parameterize this by saying r of t is equal to, now since x is your independent variable and y is dependent on x, we can just let x run as the parameter t, and then the y would be f of t. So having this parameterization, you can put it through this kappa, and then after you put it through this kappa formula, then you're going to get this new kappa formula that is just restricted to a special set of functions. Okay, so all that stuff that we've talked about with the arc length function and the reparameterization is really just the setup to get this definition here for the curvature. Once we have the definition, we're really just going to rely more on these formulas that came from the theorem that allow us to find the curvature in an easier way. So these I would kind of highlight this formula and this formula as the formulas that we're going to be using for curvature. Those are the easiest ones, at least. Alright, let's do an example. And our first example is a function that can be expressed as y is equal to f of x. So let's find a curvature at a specific point. This is going to be just as a rough sketch. This is a cubic function, and then we want the curvature here when x is equal to 1. Alright, so let's see. To find this curvature, we'll use this formula. So this is, we're going to need y prime, and that's going to be 3 1/3, that's 1. That's just going to be x squared, and y double prime is going to be 2x. Okay, so now that we have that, we'll use kappa is equal to the magnitude of 2x divided by, this is going to be 1 plus the derivative here, which is x squared, square that, raise this to the 3/2 power. Alright, now we want to evaluate this when x is equal to 1, so the kappa evaluated when x is equal to 1 is going to be 2 in the numerator, and we have 1 plus 1 squared to the 3/2. So this is 2 over 2 to the 3/2 power. We can simplify that and make it into just 2 to something, but let's just leave it like that. And that's the curvature at this point. Okay, I believe this is going to be a fairly small number, and we can see that this is a fairly not curved part of the curve. Okay, let's take a look at this one now, where we have the curvatures, or we want to find the curvature of this function. So for this, I will refer back to the second formula that we saw, which has something to do with a cross product. Just going to keep my formula to the side there so I can use that. And it looks like we're going to need r prime and r double prime. So r prime of t is going to be the derivative of this. The derivative of t is 1. The derivative of 6t squared is going to be 12t. And the derivative of 4t is just going to be 4. Alright, and then now we take the derivative of that. We're going to get 0, 12, 0. That's nice. Okay, so let's find the cross product of these two. They're kind of written so that I can see them, vertically here with the cross product. And then I'm going to have 0 and 12 times 4 in the I direction, so that's 48. And then in the j direction is negative, but it's going to be 0 anyways. This is going to be 0 minus 0. And then in the j direction, I will have 12 minus 0, so that's just a 12. Okay, the magnitude of that is going to be 48 squared plus 12 squared under square root. That seems kind of difficult to do by hand in my head. I'm going to punch that in my calculator. 48 squared plus 12 squared is 2448. I don't know if this is a perfect square. It's not a perfect square, so I'll leave it like that. There's definitely a lot of 12s happening here. You can probably factor out a 12 or a 24 and then another 4, so I'll just leave it like that. Now the denominator will be r prime of t magnitude cubed. So let's take the magnitude of the first derivative, so that's 1 plus 12t, 1 squared plus 12t squared plus 4 squared. So this will give us 144t squared, and then we have 16 plus 1 is 17 under square root. So we have a function t here, which means it's not a constant curvature, which probably makes a lot of sense, because as you go along this curve, it'll be curving some points more than others. So our kappa is going to be the square root of 2448 divided by the square root of 144t squared plus 17. So this is our general kappa. Sometimes it's a function, they write it as a function of t, which kind of makes sense, right? Because it depends on what the t value is, and whatever t value you want to put in there, you can just put into that formula, and then you're going to get a numerical value for the curvature. Okay, so that's our deal with the curvature. I hope that helps. Good luck.